Welcome to OA Week 2024. We will start in just a minute to give audience members a chance to sign in. All right, looks like we have quite a lot of participants joining us. So welcome to OA Week. My name is Katarina Shaw and I'm with the Intergovernmental Oceanographic Commission of UNESCO, as well as being part of the GOA-ON Secretariat, which is why it's my role and pleasure today to welcome you to OA Week and the session on marine chemical speciation, or MarChemSpec. Just a quick introduction to GOA-ON and OA Week. So OA Week is sponsored by 4 agencies. First of all, GOA-ON, the Global Ocean Acidification Observing Network. Second, NOAA, the United States National Oceanic and Atmospheric Administration. Third, the IAEA OAICC, which is the International Atomic Energy Agency Ocean Acidification International Coordination Center. And last but not least, the IOC of UNESCO, the Intergovernmental Oceanographic Commission of the United Nations Educational, Scientific and Cultural Organization. So GOA-ON was established in 2012 with just a handful of members, and since then has grown immensely. We now have over 1,200 members from 114 countries. GOA-ON also currently has 10 regional hubs and 1 African sub-hub in the Gulf of Guinea. The Southern Ocean Hub officially launched last week, so this is a very exciting new venture. And we'll hear from most of these hubs throughout OA Week. If you're not a member yet, we invite you to join by visiting our website, GOA-ON.org. OA Week debuted in 2020 and returned in 2021 when all events and conferences were postponed due to the global COVID-19 pandemic. Following the successful in-person symposium on the ocean in a high CO2 world in Lima, Peru in 2022, we brought back OA Week in 2023 and are now on our 4th iteration. GOA-ON has instigated OA Week to maintain momentum around OA research and to provide a virtual platform for the ocean acidification community to exchange their latest findings. We're thrilled to have a really interesting lineup of sessions again to present this week. So a little bit of housekeeping. During the presentation, all participants are in listen-only mode. You're welcome to type any questions into the Q&A box on your screen, or you can raise your hand and we will call on you to ask a question directly. This session is a discussion session, so we invite you to participate. And we will have time for questions after each of the presentations. And with this, it is my pleasure to introduce our first speaker, David Turner, an emeritus professor at the Department of Marine Sciences at the University of Gothenburg in Sweden. David is a marine chemist with extensive experience in the CO2 system and trace element chemistry. He's led interdisciplinary deep-sea expeditions focusing on ocean biochemistry. And in recent years, he has worked as a founding member of the SCORE working group, Chemical Speciation Modeling in Seawater to meet 21st century needs, to develop accurate speciation models of natural waters containing the ions in seawater. David is currently engaged in developing improved models for the inorganic chemistry of trace models in seawater and related systems. And with that, David, I'll turn the floor over to you.
Okay, thanks very much for that introduction, Katarina. I'll start now sharing. Yeah, and okay. As was said, we've got 3 presentations here about MarChemSpec, this software for chemical speciation calculations. I'm going to give an overall introduction, and then we have 2 different applications here. Simon Clegg will talk about applications to the CO2 system and MCDR, and Mattis Hein will talk about applications to paleo seawater speciation. So this is partly to illustrate we have a very wide range of potential applications here. Just like Katharina, I have a number of logos to explain from our sponsors, which you can see along the bottom here. As she mentioned, we began this as a working group within SCORE, the Scientific Committee on Oceanic Research. These are fixed-term projects, and when that ended, we moved across to the Joint Committee on the Properties of Seawater, which has 3 sponsors: SCORE, IAPSO there in the middle, the International Association for the Physical Sciences of the Ocean, and IAPWS, which is the International Association for the Properties of Water and Steam. And we are now also a project within the UN Ocean Decade with GOA-ON as our primary affiliation there. So that gives a little idea of we are. So I'll start off with the first here, the presentation, and this is not going to be a technical presentation, but I do actually have to include one equation which will turn up shortly. And this is really illustrating the way we go about calculating speciation. If you have the composition of your system and all the appropriate stability constants, then calculating the equilibrium speciation is nowadays hardly rocket science. It's a fairly simple thing to do. However, there are 2 ways of going about this. One is using concentrations here, which can be in normally moles per kilogram of seawater. And then you need this K star, a stoichiometric equilibrium constant, which is a function of temperature, pressure, and solution composition. So in other words, you need constants that have been determined in the solution you want to calculate in. This has been done for seawater for a number of systems, but that does put a lot of limitations on it, and can also lead to problems, as I'll show with an example a bit later on. The other approach is to use the thermodynamic equilibrium constant, which is only a function of temperature and pressure. But then looking at the second part of the equation here, you can see that you need these activity coefficients. And these are not necessarily easily obtained. We don't have any means of calculating them a priori. The problem is that everything in the solution interacts with everything else. And the current state of the art, which is what we're using, is a set of semi-empirical equations that were developed by Kenneth Pitzer. We say semi-empirical, they're based on sound physical principles, but there were a number of arbitrary choices that had to be made setting them up. So if we look then at the 2 ways of doing it, If we start with temperature, pressure, total concentrations, we can use these stoichiometric constants and calculate equilibrium speciation from the concentrations. And the other way is to use the thermodynamic constants and calculate the activity coefficients for the composition that you're interested in. Both work equally well. The advantage of the B option is, of course, that you can have any composition without having to have determined these stoichiometric constants in advance. And advantages and disadvantages of these different approaches. Using stoichiometric constants is much simpler mathematically. The disadvantage is you have to have measured these stoichiometric constants in the ionic medium you're interested in. And this is in some cases practical for seawater, but if you have a new solution, a new system that you haven't looked at before, it simply won't work. Using thermodynamic constants, many of these constants are well known. You can apply it to a wide range of solution compositions, and it's easy to accommodate variations in natural water composition. And you can use it to calculate new properties, looking at solubilities for MCDR, for example, which Simon will say a little about. The disadvantage, if you like, is that activity coefficients need to be calculated. This requires some expertise in physical chemistry and a sizable database. And what our aim is with MarChemSpec is to use all these advantages of the thermodynamic constant approach, but move the disadvantages away from the user so that we have the collection of parameters for calculating activity coefficient and so on built into the software, so that to be able to pick up the system and use it, you don't need the specialist expertise in physical chemistry. I've got here a summary of some speciation software systems that are in use and different, how they fit into the different approaches I've described. The one that is most widely used, I think, using stoichiometric constants is CO2-Sys for the CO2 system in standard seawater, where a lot of measurements have been made on these stoichiometric constants, and there are a whole range of different constants that have been measured. And Simon, I think, will say something about this in the next talk. There's a group that I would call B-light. In other words, they use activity coefficients that are suitable only for low ionic strengths. And this has largely come out of the freshwater chemistry community, and several of them are also focusing on binding of protons and metals to natural organic matter. For the ones that are using activity coefficients to higher ionic strengths, there's FreezeChem, which was developed for brines at low temperatures, MarChemSpec, the Miami interaction model developed by Frank Monero and colleagues in Miami. And I would say MarChemSpec, the database there is an update of the one used in the Miami interaction model, but MarChemSpec is much more flexible. Miami interaction model, you can only define pH and total carbon for the CO2 system, and you have to put in all the composition in molalities, which is not anything that oceanographers are very used to doing. FreakC is also used. FreakC can make use of Pitzer equations as well. It was developed for groundwater systems, coupled speciation and transport. It can be used for seawater. My experience is it's rather fiddly trying to use freak sea for seawater. And then there's a system called the Geochemist Workbench, which gives access to a lot of the databases in these systems. So a bit more on MarChemSpec, what this will do. It's easy to get hold of. The software is in a Zenodo archive, and you can get at that from our website. Fully documented. See, for the seawater electrolyte and tris buffers, from our published papers, you can see the sources of every constant and parameter that's in there. So the documentation is there if you want to look at that. We're using Pitzer equations with the most up-to-date parameters that we have found. And for the key results, we also have estimates of uncertainties in the results. And user-friendly, you can run this from a command prompt using text files, or it can be called from Python or MATLAB. We also have a draft wrapper, as it's called, communicating between the programming environment and the calculation engine for R. And if anybody is a good programmer with knowledge of R, please let us know. We'd love to have some help in testing that out and being able to release it. So our current capabilities, on the seawater electrolyte, in other words, the species you can see down at the bottom here, from 0 to 45 Celsius at 1 atmosphere pressure. We have trace metals included in the present release. And I've put here that the trace metal part is provisional. I am in the middle of revising it. So we hope then during the spring, we'll be able to release an updated and improved version for trace metal speciation. So what do you need to put in? For seawater calculations, you just put in salinity and some of the 4 CO2 system variables, and you can do very simple calculations that way. For any other system containing some or all of the elements we've shown, it could be just seawater with unusual compositions. So you need the total amount of each solute and also CO2 system variables. And you can also put in total amounts of trace elements in any of these. The outputs you get, molarities and amount contents, which I've learned is the official term for moles per kilogram solution of everything. pH, partial pressure, viscosity of CO2, alkalinity and total inorganic carbon, stoichiometric constants, and concentration products, calcium and carbonate. And there's a potential for looking at additional solid phases. So it's very flexible in terms of what you can put in input, and you get a very detailed set of output. Now, I just wanted to show one example of this, and this is looking at pH along an estuarine gradient. So I've done this, as you can see, for 10 Celsius and PCO2 of 423 microatmospheres, which is about what it is today, global average. And I've taken 3 different cases for fresh water here. The red one is pure water. and this is effectively what CO2 cysts will give you, because you can't put in any freshwater composition there. At the other end, the blue one is a high alkalinity freshwater with an alkalinity of 3,000 micromoles per kilogram. These are freshwaters draining chalk environments. I've picked on the figure of 3,000 because that comes from what I might call my oceanographic backyard here, the Baltic Sea. The freshwater inflows to the Gulf of Riga have about this alkalinity. So you can see there you have a high pH, which then tends down towards the seawater pH. In the middle is something that probably doesn't exist, world average river water. So you can see that away from the extremes, the changes in pH along the estuary there are not actually that great. But this is an illustration of the flexibility of MarChemSpec, that you can put in these different freshwater and members. So I'll just finish by saying what we're up to at the moment with further development. For tris buffers, we're working together with national metrology institutes in Japan, Germany, and the United States to create an accurate model for calibration of total pH and conversion between total and free pH. For the natural waters, for the seawater electrolyte, we're looking to improve the accuracy with some revision there and an extended treatment of uncertainties, and also looking at developing teaching material that makes use of MarChemSpec. I'll stop there. You can see on here our website address where you can find a lot of information, download the software, and if you have questions outside this session, anything concerning the code and the seawater electrolyte, that's best directed to Simon, and for trace metals to me. So I will stop sharing there now, and I see there are two chats here.
Yes.
Okay, that's from you,
general
Catherine.
Messages to the public who've not responded. So if you have any questions to David, please feel free to raise your hand and we can call on you if you want to ask your question directly, or else you can use the Q&A box or the email addresses that were just provided. We will also put them in the chat in a minute. If nobody wants to go ahead, we'll have a few minutes after the presentations as well. So following the presentations, there'll be time for more questions if you need to ruminate on this. No one
Well, that
did?
was either amazingly clear or it's taken time to sink in. I don't know which.
We will see.
Yeah.
Excellent. Thank you so much for that, David. And with that, I would like to introduce our next speaker. We now have, hang on, here we go. We will now move on to Simon Clegg, Emeritus Professor at the School of Environmental Sciences of the University of East Anglia in the United Kingdom. And Simon is a solution chemist with an interest in chemical speciation in natural waters, including gas, liquid, solid equilibrium and atmospheric aerosol systems. He is one of the first to develop an ion interaction model of seawater chemistry. In recent years, he has worked as a founding member of the SCORE working group's chemical speciation modeling in seawater to meet 21st century needs, and to develop accurate speciation models of the tris buffers used to calibrate the total pH scale and of natural waters containing the ions of seawater. He sees increasing practical needs for such models within chemical oceanography, but unfortunately, a decline in the skills required to develop and use them. So Simon, the floor is yours.
Replace current share. Okay. Okay. I'll assume we have the correct slides up now.
Looks great, thank you.
And pointer options. Laser pointer. Okay, so I'm going to talk now about two carbonate-related applications of the model. One from our previously published work when we were developing the model, and another from more recent efforts. So this is modeling the dissolved CO2 system. We're going to look at one of the constants, and then mineral solubilities in natural waters affected by MCDR activities. And rather like David, my purpose here isn't to tell you about hot new science. Rather, it is to show the kinds of applications in which a speciation model is a valuable tool, and which it indeed is essential for. So let's move forward. On the right-hand side, we have this diagram of our friend the carbonate system and its various equilibrium reactions here, here, and here. And below that, at the bottom, a list of seawater species in the model, the major ones in black, all of the acid-base ones in red, and then some ion pairs along the bottom, and these are also dissolved species. And the two things that we're going to look at in this talk are, or to address the questions of which set of constants is preferable. There are many sets of carbonate constants available, too many, some would say, and a lot of effort has been expended into determining the most self-consistent and accurate set. So the model has some very useful insights into which are better, even though it is not yet as accurate as the best constants, whichever they are. So you might ask, what then is it good for now? Well, one of its principal value is calculating the effects of changes in seawater composition on carbonate and other acid-base equilibria and trace metal trace metal complexation, and also properties such as solubilities. So that's our first question. The second thing we're going to look at is dissolving alkaline minerals in seawater. So one of the MCDR interventions being researched is the addition of soluble alkaline materials, and at and close to the sites of these interventions, it seems likely that seawater composition and chemistry could be quite disturbed. And a couple of important questions would be, first of all, how much is alkalinity reduced and seawater drawn down from the atmosphere for adding different minerals? And then what are the effects locally on solubilities of various soluble, sparingly soluble solids, minerals in seawater, and what does it do to pH? So we're going to look at that too. So first, dissolved CO2 constants, or rather one of them, the dissociation of bicarbonate. It's a rather busy slide. First, in this box 1, there's a list of the equilibrium constants. Each has been measured in seawater and is available as fitted equations as functions of salinity and temperature. And there are the three constants. pH is on the total scale. And here in this this graph, so this is related to the many sets of constants that are available for calculating equilibrium from pairs of values of the 4 carbonate variables: pH, total alkalinity, dissolved inorganic carbon, and PCO2 or CO2 fugacity. And the plot is of a rather complicated mean uncertainty ratio, which is showing of calculated versus measured values from combinations of pairs of these the carbonate system variables taken from ocean observations. And to cut a long story short, lower is thought to be better. And there are, I think, 16 different data sets for K2 along the bottom, and I've starred the ones which are all of the lower values. So the questions are, which set is more nearly correct, and how would we know that? And then these are for typical ocean salinities, but what happens at low salinity? Do we know the constants there? And what happens, of course, if we depart from seawater composition for some reason? And the reasons for pursuing accuracy are to disentangle or investigate other complicating factors, such as organic alkalinity. And one of the difficulties we have with all the sets of constants is, to go back to the questions above, what happens at the site, say, of MCDR interventions or in various natural waters around the world, where the seawater chemistry may be very much changed relative to normal seawater stoichiometry. Which is to say, I mean, to go back to David's slide contrasting the two approaches to calculating equilibrium, all of the constants which have been carefully measured in seawater for these altered compositions, either naturally or artificially, they're not going to be correct. And we'd love to know how these constants are going to differ. And the speciation model gives us a way of determining that. So let's just compare, use the model to compare a few data sets for K2, the dissociation of bicarbonate, its function of salinity at 25 degrees. And here's the expression for it. There's pH, total dissolved carbonate. You'll see that in modeling terms, the ion pairs are included in that total, and then bicarbonate on the denominator here. And there are some key points to be aware of in what I'm going to show you. First of all, really using the model here as an arbitrary reference. So it does have known limitations, which we've explained in our papers, and it will, in general, be most accurate at the moment at low salinities. So the purpose of its use in this presentation is mainly to look at how the data compare with each other. I say mainly, not entirely, but mainly. And we're not comparing all data sets here, all of those 16, only a sample of those which show well on that previous plot, namely have small values on the y-axis, and those that show poorly. So let's do that for a few data sets. So here we have the measurements of Roy et al. One of the less good data sets on the earlier plot showed as measured minus calculated values of K2 against salinity here. And the shaded area is the expected MarChemSpec model uncertainty, assuming that its underlying parameters are complete and essentially accurate themselves. And we can say right away a few things looking at this comparison. One, the result singular at low salinity is simply implausible. We know from the way these models work and the thermodynamic relationships that this is simply not going to happen. So we know there are problems below a salinity of about 10 or so. And the higher salinity results, well, they are a long way from the model. So, I mean, we would, without doing any other comparisons, generally think of these as somewhat doubtful. So next we move on to a second comparison. The Roy et al. Data are still here on the graph, but they're grayed out. And we've added the work of GOA-ON and Poisson, also one of the less favored data sets generally within the community and from that first plot. So what can one say about them? They agree rather well actually with the Roy data, but there's a great deal of scatter. And really in the without any other comparisons, that's about as much as one can say from them. So the next step is to add one of the sort of more favored data sets and see how that compares with the other two. So this is the work of Malero et al. Over a wide salinity range, and now we see both quite precise measurements, not so much scatter, significantly different from Roy et al. And Poisson et al. It's down in the model range, but also here, the line is Malero et al.'s fitted line. The results at very low salinities, below 10 or so, below 5 or so, are implausible, and it seems that the fit has been rather distorted by these points here. And in fact, it's not as good as one would wish, even at normal seawater salinities. So as one last step, I'll add one of the other generally favored data sets, a more restricted range. This is the work of Luca et al. And we can see the red squares here. They agree very closely with the Malero data. And we see that their fitted line reproduces their own data well enough. But in fact, you can say the data agree better than the fitted equations from the two authors. And the problem is really the fit of the Malero results, which don't agree with those results, with their results at as well as would be expected. And that's not something, I mean, surprisingly, that anyone has delved into before, as far as I'm aware. So to conclude, I mean, I think I can be confident in saying that for low salinities, below 10 and particularly below 5, I think that in general, the model is giving more accurate results than have so far been achieved experimentally. And David is more of an expert on the measurements than I am, but I suspect that one of the factors is that the alterations of the composition of the medium at very low salinities are are in the experiments are necessarily quite significant, and that may bias the results. But I'm just throwing that out as a suggestion. So let's move along to look at a simple MCDR application that we dreamed up, alkalinity enhancement by mineral dissolution. Well, there are existing papers on it. And we just ask the simple question, what happens at or near the site of a mineral addition? Now, because MarChemSpec calculates chemical equilibrium, i.e. there's no treatment of transport processes, we think of the problem in a very simple way, which is in this box here. There's two steps. First, we add the mineral. The mineral dissolves, and the altered seawater comes to some new equilibrium with respect to carbonate and the other acid-base species, and a reduced equilibrium PCO2 because of the increase in alkalinity. Then we allow CO2 to be taken up from the atmosphere to restore equilibrium with the atmosphere, and a new composition here is achieved as the CO2 dissolves and there's an increase in the dissolved inorganic carbon. So what are the properties of this seawater and then this seawater? Now we can calculate, using the speciation model, really anything that involves a concentration or an activity, which means we can very easily obtain the change in total pH, dissolved inorganic carbon, saturation with respect to calcite, indeed saturation with respect to any other solids we might care to calculate, as long as we're able to estimate the thermodynamic equilibrium constant. We can also do changes in trace metal complexation, but that's not a subject of this talk. So for example, for our example, we decided to calculate the properties of the two altered seawaters, seawater plus mineral and seawater re-equilibrated with the atmosphere, for the addition of these 5 minerals, forsterite, portlandite, brucite, calcite, and dolomite. And I have just a couple of slides on these to follow. So here are our results. So you first look at this table. We describe the addition and alkalinity here, a constant 0.2 millimoles for the 5 different minerals, and that's about a change of only about 10% of normal. And the first step, the addition of mineral and dissolution, has this yellow-orange background. And then the second step, after re-equilibration with the atmosphere, these results in blue. And we see that at the first step, saturation with respect to calcite goes up from about 5.5 to 8.5, and then falls back after re-equilibration with CO2 to a slightly greater value of just over 6. Total pH goes up from about 8.1 to greater than 8.3 when the mineral is dissolved, or when this amount of mineral is dissolved, and then falls back to almost the same value after CO2 uptake. And the first 3 compounds listed, the brucite and was it portlandite and the forsterite, yield the greatest uptake per gram of material added. That's uptake of CO2. So it's about 0.02 moles of carbon per gram of added material. So now let's just focus on the addition of one of those minerals. So addition of brucite, which is the magnesium hydroxide. And so what we have on the left, this is a graph of what happens to total pH for for quite large additions of brucite, up to 5 millimoles roughly per kilogram of seawater. And you see here for 2 millimoles added, we start, the brucite is added to the solution, it dissolves, and we're at this point here where the pointer is. And the pH under these circumstances, without anything else happening, would go up to 10.5. And then as CO2 is taken up from the atmosphere, it would go back and it would settle at about 8.4 or so. So that's quite a large change. Now on the right, we see the calculated degree of saturation with respect to calcite for the same process. And the black arrow here, I placed it at about 1.5 millimole of added brucite. And after it is added and dissolves, well, this would create, without anything else happening, a calcite supersaturation of about 40, which, so precipitation is likely to happen there. And even after CO2 is taken up from the atmosphere, for such a solution, it would fall back to about a factor of 20 or so. So, I mean, because in reality, presumably calcite would solidify and form out and fall out of the solution, the solid would form. This is actually the dynamics of what will actually happen are quite complicated. And I should say, one thing I'll leave open for you. I know why the degree of supersaturation levels off and doesn't increase beyond about 2 millimole of added brucite. I'll leave you to guess why that would be. And finally, something we didn't show, calculation of saturation with respect to other solids. I mean, one in particular that we did for our own interest, mixed magnesium hydroxide chloride, also has been found to yield supersaturation on initial dissolution of the added solid, and then subsaturation after the CO2 uptake. So there'd be complicated things going on in the addition of a real mineral to seawater, especially if it's done to a high concentration. So try and emphasize that this is not really a complicated calculation. So how do we do that for MarChemSpec here? So the procedure is simple. So for step 1, which was addition of the dissolved mineral, enter the temperature and then the solute composition of the seawater of the appropriate salinity, plus added amounts of ions from the dissolved mineral. So for brucite, it would be extra magnesium and extra hydroxide to the amounts already present. And that's the first calculation. And then for the addition of dissolved mineral plus drawdown of CO2 from the atmosphere, do the same as one above, but then also enter in the data file or in the call of the MATLAB or Python routine the desired PCO2 that we want to equilibrate the solution to. And that's it. And for calculations of degrees of saturation with respect to solid phases, such as calcite, well, the appropriate method here, where the seawater may have a different stoichiometry from normal due to the additions, is to use a thermodynamic equilibrium constant and calculate a saturation ratio from the actual molalities or amount contents, well, molalities in the first instance of the calcium and the carbonate and the activity coefficients. But that is relatively straightforward. So a couple of final notes for MarChemSpec capabilities, and this is my last slide. The model, it calculates all of the acid-base equilibrium constants, the K star, for seawater acid-base equilibria automatically. Those are part of the output. Saturation with respect to solids needs to be calculated by the user with a knowledge of the appropriate equilibrium constants. So that's a bit of physical chemistry the user has to bring to the model. And in applications where the carbonate system equilibrium is important and of interest to the user, it's most suited to determining the effect of composition change in the medium relative to values for seawater. And in that way, the small systematic errors that remain to be eliminated from the model have much less effect if one is calculating simply this relative change, the value for seawater and the difference between that and the value for the natural water of interest. So the model has the solutes of seawater, the iron, sodium, the chloride, all the rest built in. But if you're interested in other species and other equilibria, they can be added straight from text files. It requires a bit of, well, more knowledge of the physical chemistry than any technical knowledge about the model, but the user can add these quite easily. We did this, for example, because we were interested in the effect of borate complex formation in some of the solutions actually used to measure borate equilibrium constants in seawater. So that is relatively easily possible, and we can show people how to do it. So I think with that, I've come to the end of this very short look into a couple of capabilities of speciation modeling in general, and also what we can do with MarChemSpec. So thank you very much.
Thank you, Simon. We do actually have a few questions that have popped up in the Q&A box now. The first question is, can we use David's equation for activity coefficient? And Kishore, if you want to ask the question live, you're also very welcome to raise your hand and we can call you. Excellent, here we go. Hang on, give me a quick.
Yeah.
There you go. All right, Kishore, you should be able to speak now.
Can you hear me, please?
Yes, very well,
Yeah.
thank you.
So, David, that was a
Yeah.
very interesting talk, to be honest with. Thank you very much for that. Because I was just wondering, because I'm a marine chemist, normally we do ocean acidification in Mauritian waters. But then we were coming up with this paper and we had to calculate the activity coefficient for H plus and for the other ions. But do you think it's worth using Davy's equation in this case?
I mean, the problem with the Davis equation is that it aims to calculate activity coefficients just from the ionic strength.
Right.
And it was developed to work up to an ionic strength of about 0.1. And in many cases, it gives a reasonable answer there. But as you get to higher ionic strengths, then the Davis equation becomes less and less accurate, because the activity coefficients are beginning to be dominated by specific interactions between some of the dissolved species. So that if you get up to seawater ionic strength, then there are significant errors in using the Davis equation.
Okay. Okay. Thank you very much. Cheers.
Katharina, I can have a go at the second question, if that's okay.
Go ahead, please.
Or I'll have the first go. That if you don't know all of the concentrations of the constituents in your solution, what do you do? Should you include what you know, or should you only include concentrations if you have the full picture? Well, I can think of one has to look at the kinds of, well, a couple of different cases. One would be, let's say you have seawater in which you know the composition with respect to all of the major species, but let's say you're interested in some very minor or trace constituent, which you believe is there, but you're not sure exactly what the concentration is. Well, under those circumstances, we know that the activity and any equilibrium constants which involved this trace species would be determined by the major species there. So you could calculate them without knowing exactly what your trace species concentration was. So that's one case. The other would be, that's occasionally useful to us, is we know the solution is relatively complicated. I mean, one could take seawater as an example, and we'd say we'd want to simplify. How would we simplify this? If there were some constituents, significant constituents, which we didn't really know they're much about, and under those circumstances, one might try to keep a constant ionic strength through substitution, say increasing the amount of sodium chloride or decreasing the amount of sodium chloride, to be like the medium, closer to the medium you're expecting. Now that's probably a somewhat incomprehensible answer, but the main thing to take from this is that there are possibilities, but it depends on your exact situation. There's no one answer to that question under all circumstances, but yes, there are answers. I see Mattis has put his hand up, so I think he wants to add something.
Yeah, I just wanted to point out that I will be discussing one of those use cases where we only know some of the major ion composition of the past oceans. So I'll talk about that a little bit.
Okay, thanks, Mattis.
Brilliant,
David, do you want to address the
Yes,
organic?
I can take the next question. I don't know if its question is going to come live, or I should just answer what's on the Q&A.
you mind reading it out and then answering it? Because the audience
Yeah.
can't see the question right now.
Okay. So it says, thank you for your impressive presentation. Well, thank you. Do you think it'd be possible to include the contribution of organic alkalinity to total alkalinity in MarChemSpec? And if so, how could it be achieved? Yes, that is an excellent question. And we would very much like to be able to do that. We're not there yet. To give a bit of background here, in fresh waters, where you have a much higher amount of natural organic matter, there are generic models for the interaction of protons and trace elements with natural organic matter that work reasonably well. And there is work going on now to try to adapt those models to the natural organic matter in seawater. This is much harder because there's much less of it. And it means the whole question of sampling and characterization is much more difficult. But 2 members of our chemical speciation group are working on this and working towards developing a model for seawater, a generic model that can be used. And we're also thinking about how we could be able to adapt that into MarChemSpec, because it's a very different sort of chemistry for these natural organic matter. So the answer is, we'd love to do that. We're working on it, but it's not going to be that quick, I'm afraid.
Does that answer your question, Song Su-Shin? Or would you like to ask a follow-up? We're good? Okay, thank you. We'll take the next question then. This is not addressed. Excellent. Thank you, Song. So this is not addressed to anybody in particular, so I'm just going to read it out and then we'll see who feels up to answering. There are many studies that have looked at secondary calcium carbonate precipitation during ocean alkalinity enhancement, and they've typically calculated omega using CO2 sys. How much is the interpretation of these results changed when accounting for changes in seawater composition using the MarChemSpec model? Simon, you want to go?
Yes, I expect David and possibly Mattis might also want to, but I'll have a go first. I was thinking about this question as I was looking over the slides, wondering to myself, if I did this with something like CO2 sys, how much would things change? And without having done that, I would say the thing that concerns me, well, there are 2 aspects. If the seawater composition isn't going to be changed very much, namely if the dissolved addition is small, then one would naturally expect the alteration with respect to pure seawater to be also small. But if it's large, then I think the biggest changes, or the minerals for which one would most need to worry, would be those which were magnesium containing or possibly calcium containing, because these both in the solution interact very strongly with the carbonate that is there, and that would, I think, alter the carbonate system equilibria. So that is that's my first take on that question. So David, Mattis, do you have a point to add?
Yeah, I mean, of those 2, magnesium is the bigger problem, in that its interaction with carbonate is somewhat stronger than calcium. On the other hand, there's a higher ambient concentration of magnesium already, but those are probably the 2 main ones.
And if I can add to that, it certainly depends on the type of mineral you're dissolving. So if it was to be magnesium chloride, which has a is basically just changing the divinyl cation concentration, then that will require something like MarChemSpec. If you were to use magnesium hydroxide, then probably the hydroxide will have a larger pH effect than the relatively small change in magnesium of that seawater. So, so for a basic mineral, the base from that mineral will dominate the effect. So for relatively small additions that don't substantially change magnesium, it would seem appropriate still to use CO2 cis or something similar. However, after equilibration with CO2, when the pH signal is worn off, you could potentially have a much larger change in how much mineral you've added to that water. And so eventually you will reach the alteration of the seawater that requires Pitzer modeling.
Thank you all for that. Michael, has that answered your question? Would you like a follow-up? If so, please raise your hand. If not, we will proceed with the next presentation. All right, no waving from Michael.
I am sharing.
Excellent. I'll give you a quick introduction to our next speaker, if you'll allow me. Next up is Mathis Hein, Associate Professor at the University of California, Santa Cruz. Mathis studies the operation of global biochemical cycles in the Earth system. Mathis has made contributions to our understanding of ocean regulation of atmospheric CO2 and ice age climates of Earth's recent geological past, and he contributes to the reconstruction of ocean pH, atmospheric CO2, and climate for long-gone greenhouse worlds that may be analogs for future warming. A recent focus of this work is on numerical simulation of ocean-based intervention strategies to mitigate anthropogenic carbon emissions by purposeful carbon dioxide removal, to compare their relative effectiveness, quantify ocean acidification co-benefits, and to assess a diverse range of possibly adverse side effects. Mathis, the floor is yours.
Hello all, thanks for joining today. So I will be taking the session into a slightly different direction, talking about Earth history, and what I really hope to convince you of with my talk is that using Pitzer modeling is critically important for our understanding of the long-term carbon cycle. Okay, so my perspective is slightly different. So I am interested in the global cycling of carbon between CO2 in the atmosphere and dissolved inorganic carbon of the ocean. And I use carbon cycle models to simulate the cycling of carbon in our surface environment. And so there's a number of things that go into carbon cycle models, and most of them are sort of showcased here in this diagram. I do want to point out a couple of features here. So first off, we have a carbon cycle that is within the surface environment. So carbon being exchanged between land carbon storage, atmospheric CO2, and ocean dissolved inorganic carbon. There's biological carbon cycling, of course, on land, but also in the ocean through the ocean's biological pump. And biology in the ocean, the two fundamental vectors of change or of biological effects are through the production of organic metabiomass, but also calcium carbonate. So a lot of organisms produce calcium carbonate hard parts. And then this calcium carbonate, eventually some portion of it gets redissolved in the ocean. That's most of the calcium carbonate production. But on the other hand, there is some calcium carbonate preservation on the deep sea floor. So that's the dominant carbon sink in our surface carbon cycle. And in the modern ocean, we have carbonate burial roughly equally split between calcium carbonate aragonite dominantly on the continental shelf and reef systems, whereas deep sea calcium carbonate burial is dominated by calcite. Okay, so if I want to simulate a carbon cycle like that, of course, I care about the cycling of carbon, but in order to calculate some of these production of calcium carbonate and dissolution of calcium carbonate, as well as the CO2 exchange with the atmosphere, I need to solve carbonate chemistry. And so my background has been primarily in studying ice ages of the Pleistocene. And over this time scale, the last 2.5 million years, we can basically assume that the major ion composition of the seawater was relatively constant. So that is good news for me because I can use the stoichiometric equilibrium constants that Simon mentioned that are valid for modern seawater for the entirety of the Pleistocene. And I can simulate the carbon cycle. I don't have to worry about changes in the major ions of seawater. All the model needs to really track are changes in alkalinity, shown here as in the left diagram as the difference between conservative positive and negatively charged ions. That is basically what drives the pH-dependent speciation of weak acids in seawater. Okay, so if I can use modern ocean seawater constants, everything is easy. I just take my carbon cycle model, I use empirical constants, and there we go. So that works great for ice ages. However, and so these diagrams are from this new chapter that I just wrote. However, we've known for some time that that the surface carbon cycle has seen dramatic changes, not only over the course of the Phanerozoic, but Earth history. And those major changes seem to correlate with supercontinent creation and supercontinent breakup. And so it was recognized for a long time that during, while the primary mineralogy of calcium carbonate by reef building organisms in the modern ocean is aragonite, that back in the Cretaceous and the Cambrian, Ordovician, Silurian, Devonian, back in the Cretaceous, we had a calcite type mineralogy on the continental shelf. So there's been a long-standing debate about whether or not this is related to changes in the carbon cycle or changes in seawater composition. And it was Hardy and also Stanley and Hardy that basically provided like striking evidence for changes in the major ion composition of seawater, hypothesized by this creation and breaking up of supercontinents. Okay, so over the last 80 million years, seawater composition of seawater has changed dramatically. Okay, and there's some more recent work on that, and I just wanted to highlight here a recent paper by Leedy, and so in the Cretaceous, when Pangea started to break up, we had lots of fast spreading ridges, but in the modern ocean, if you look, there is this very slow spreading Gackel ridge. It's actually so slow spreading that very little basalt is being formed. So there's a very thin basaltic crust, and seawater can directly interact with mantle rocks. So basically, for the last 80 million years, it seems like this ridge system has been drawing calcium down and enriching magnesium in seawater. And so that's the primary information we have on these changes in seawater is sort of summarized here on the right-hand side. So we have substantial changes in magnesium-calcium ratio of seawater. somehow related to plate tectonics. And so we have magnesium, we have calcium. We basically do not know very much about all of the other major ions. Okay, so that's a real problem. But let's work with this. So I borrow here a slide from David's presentation where I'm just going to ask. So 10 years ago, I wanted to simulate some of these chemical changes. And of course, I cannot use CO2 because that's only valid for modern seawater. Of course, I cannot use these models that are only valid for freshwater or low ionic strength solutions. And so I have to go the full Pitzer way. And so looking at these options, the freeze chem option, that's for low temperatures and ice. And so that's not completely relevant in my case. The MarChemSpec model was not yet available. So that's new. That's from last year when it was published. The Miami model developed by Frank Millero and colleagues was available as a Excel sheet. And FreeQC was available as a source code, but as a code base, but it's primarily used for groundwater. So it's not completely clear if it's applicable to my seawaters. In addition to these Pitzer type models, there's also an older type of set of correction factors by Benyakov and Goldhaber, 73, and then there was an extension made by Tyrrell and Zeeby in 2004. So these are the options that we have, or used to have, the options that we have in order to account for major ion composition changes in seawater through Earth history. And so just looking at these correction factors first, just to get an idea of the size of the changes, the magnitude of change. So what I'm showing here in these panels is changing magnesium concentration on the y-axis, changing calcium concentration on the x-axis. And I'm showing some of the most important equilibrium constants, the solubility product, K1 and K2 from Benyakov and Goldhaber are all changing on the order of tens of percent across this solution space. And looking at the KSP, the solubility product for calcium carbonate of Tyrrell and Zeeby, what I discovered was that it is doing something very bizarre. And that is because they fitted a magnesium-calcium ratio dependence. So basically only if the ratio of these two changes, the solubility product changes. And so because of that discrepancy, I felt I could not use the correction factor approach, and I needed to do something else. And so I basically looked at the Frank Millero's Miami model, and so that was available as an Excel sheet, but that's not going to work for my carbon cycle modeling. I need a more usable code base, so I implemented the Miami model in Python and adjusted a whole bunch of the parameters in order to do Pitzer type modeling for paleo seawater. Okay, so this is the result here, what you see at the bottom, and what you find is that there are some significant differences, not only with the Tyrrell and Zeeby correction factor, but also with the older Benyakov and Goldhaber data. And so there is a real change in equilibrium constants that we need to account for in order to reconstruct or simulate the carbon cycle of the geologic past. Okay, so now I'm going to compare a little bit against the other options that we have. So this is now the Miami implementation of the Millero model versus FreeQC, which is supposed to be good for groundwater, but when I try to use it for this purpose, I found that it is doing a very poor job of reproducing the empirically determined stoichiometric equilibrium constants that are valid for modern seawater. So this is using Pitzer models to trying to replicate what has been empirically determined on modern seawater. And Miami is doing a reasonable job of reproducing the speciation of modern seawater, unlike free QC. All right. Now, of course, we are pushing ahead using MarChemSpec, and I wanted to point out that in Miami, the way that I developed the interface was to only allow calcium and magnesium to be changed under the assumption that all other major ion of seawater stay at modern concentration. Now, this is an approach that actually doesn't quite work for MarChemSpec, where you need to specify the full solution composition. But what I want to point out is that both the more comprehensive MarChemSpec and the somewhat simplified Miami implementation are in reasonably good agreement, and that is largely due to the fact that we're drawing on the same thermodynamic database. Okay, so the model implementation seems to result in quite similar results, and this intercomparison is work that my graduate student Terigani is working on, and she is doing that specifically to look at paleo seawater concentration. What you see here in the sort of grayed out dashed lines in the background, that's Miami, compared to MarChemSpec across a huge range of calcium and magnesium ratios. Okay, so for MarChemSpec, we now need to make a slightly different assumption to calculate these than in Miami. So instead of holding all other major ions constant, in MarChemSpec, we are actually holding the ionic strength of seawater at a nominal salinity of 35 constant by adjusting sodium chloride. So this is slightly different ways of calculating this. I want to point out that for KSP, K2, and KB, the models agree very well. There are some significant deviations for K0, K1, and Ks, but all three of these equilibrium constants only change on the percent level, a few percent level. So even though the contours are tilted here quite substantially, these are relatively small changes compared to K2, KB, and KSP. Okay, so we're talking about relatively large changes in equilibrium constants that could happen, that will be the result of changing major ocean, major ion composition of seawater. Okay, so using Miami, we can do a couple of things. So first is we can try to reconstruct the carbonic chemistry and speciation of past seawater using the boron isotope pH proxy, which requires knowledge of the boric acid equilibrium. Okay, so we're using an indirect method to reconstruct the pH of seawater and use that also to reconstruct carbonic chemistry and atmospheric CO2. So some of the things that need to go into this calculation are shown here on the left, and I want to highlight in the top panel, the boron isotopic composition reconstructed on the shells of foraminifera, and this is work by Cindy Asosdian. And then I consider changes in calcium, magnesium of seawater, changes in the saturation state of the deep ocean, as well as background changes in the isotopic composition of total boron in seawater. And propagating these uncertainties as quite a computational challenge. So I made sure to have a scenario where we assume constant seawater composition and one where we account for the recent trend in calcium and magnesium. And what you can see here, if you go back as much as 20, 25 million years ago, we are suggesting that maybe a quarter of the surface carbon inventory was removed at the time, also yielding an ocean that was less alkaline, but overall still has somewhat elevated CO2s. The saturation state of the ocean over the last 20 million years is relatively flat by comparison. Okay, so this is speaking to the carbon cycle dynamics that maintain the climate system and saturation state of the ocean are propagating changes in the seawater major ion compositions to yield large changes in carbon inventory, pH, not so much saturation state, but atmospheric CO2. Okay, so having pioneered this approach, the Miami is now a standard tool used by the boron isotope pH proxy community. And for example, Miami is also underpinning the recent Cenozoic timescale CO2 reconstruction by a large international consortium. So I'm glad to report that the boron isotope pH proxy community has adopted Pitzer modeling for their work, and so that's one important application. The other, of course, is that we want to use Earth system models, carbon cycle models, to simulate the carbon cycle of the past. And so these carbon cycle models internally also compute speciation, assuming some set of equilibrium constants. And one of the most widely used models, the CGNE, or Earth system model of intermediate complexity, has built-in correction factors that I showed you earlier, based on Ben-Yakov and Goldhaber and Terrell and Zeeby. And so updating these somewhat deficient equilibrium constants, just for modern seawater, they were using a pretty old set of equilibrium constants, and just updating to Miami changes the simulated modern carbon cycle. And you can see some of the changes in the equilibrium constants up top, and then some of the changes in ocean carbon concentration, pH, and saturation state at the bottom. This is for a closed system carbon cycle response. So before calcium carbonate burial into solution adjusts the ocean's alkalinity budget. And this is work, this implementation of Miami is work of Marcus Adloff, who's a postdoc in Bern, and Tara and I have been helping out with porting the Miami capabilities into the CGNE model. And we have a code base where we use MarChemSpec constants in that model framework. So that's also going to come out soon. But to give you an idea just how big those effects are, once we consider seawater of the geologic past, I'm using here the Eocene ocean as an example. So if we were to assume calcium and magnesium concentrations from the Eocene, we're seeing these very large changes in the equilibrium constants and huge changes in the saturation state and pH. That they're really significant. Okay, so this is what happens to a carbon cycle if you suddenly change the composition of seawater without allowing the open system calcium carbonates. If we, and to sort of summarize here, so that before we added this Miami-based Pitzer modeling equilibrium constants to CGNE, you'd have the non-outline bars, changes in equilibrium constants and changes in speciation of seawater. Whereas with Miami, you're getting different results, and significantly different results, in particular for the saturation state of the ocean. So if we go to Eocene seawater composition, suddenly the ocean would be about twice as saturated using Miami, but more than 2.5 times more saturated using the previous correction scheme. And so we are going to see large changes in the global carbon inventory and global carbon budget once we integrate that using a carbon cycle model that takes account of the open system dynamics. So we have 2 dynamics. We have the calcium carbonate compensation feedback operating in the carbon cycle, where a change in if there's more weathering on land, more alkalinity brought to the ocean, then there is burial of calcium carbonate that will raise ocean pH, that will raise the saturation state of the ocean, that will increase calcium carbonate burial on the deep sea floor, and thereby stabilize the ocean's alkalinity budget. And on even longer time scales, we have the silicate weathering feedback, where if there's more CO2 coming out of volcanoes, it will lower the ocean's pH. A lowering of ocean pH will raise CO2, and higher CO2 will warm climate, and warmer climate will lead to more silicate weathering, so as to balance the silicate weathering with volcanic CO2 sources. So accounting for both of these dynamics now, what we estimate is that the Eocene ocean probably had on the order of about 1,000 gigatons of carbon more than the modern ocean, and that is significant downward revision of previous estimates using the correction schemes, where the Eocene ocean would have had almost 3,000 more gigatons of carbon. And so with this little whirlwind of effects, I just wanted to summarize what the key take-home points are here. And the first one is that the Pitzer models that we have from the last, say, 25 years, they all yield a significant revision to the carbon and speciation correction schemes that were previously used in the scientific literature. All of these Pitzer-based models, the Miami model and my implementation thereof, and the MarChemSpec model, perform rather similarly. They differ at the percent level. I would, from my perspective, I would have been very happy if MarChemSpec had been around 10 years ago. I would have saved myself a lot of work by just adopting it. It's the most quality controlled and most comprehensive code base we have today, and I can wholeheartedly recommend it for any paleo seawater application. Thanks for your attention.
Thank you for that presentation and for the ringing endorsement. That was quite the case studies you showed. We currently don't have any more questions, but if people would like to raise their hand or quickly type a question into the Q&A box, we do have a few minutes yet.
Ooh.
And in the meantime, Simon, please.
If there's a question either articulated or not out there, which is how does Miami model differ from MarChemSpec? As David said, we started with well, Miami was the starting point, but as we went through the different papers, the different tabulations of coefficients for the model, we checked that they A, made sense, B, were correct, and references to them were consistent across different papers. And you know, it's a big, complicated piece of work which has evolved over very many years. So there were quite a few errors and occasional cases where we were not able to make sense of what was published, and so we had to revise certain of the interaction parameters ourselves by going back to original data. And that is the fundamental difference between the two, apart from the fact that MarChemSpec also has at least the good beginnings of a internal estimate of uncertainties on its outputs, which I think we're the first PITSA model to have. So in short, we believe MarChemSpec to be better quality controlled and more accurate and more correct than was Miami. I think that's a reasonable statement to make. So thanks.
Yeah,
Thank you
maybe
for
I
that.
can add
Go
to
ahead,
that a little bit. So I encountered a lot of these inconsistencies in the tabulated parameters that were in the published paper versus the original literature. So I dug through a lot of that. And there are also, I found at least one, maybe I can just share that. If I go back a couple of slides here. So where you see an X in this table, I'm using the same original reference as the Miami model. But where I have a number, I've changed the data source. And specifically, I had to go back and look at the calcium to bicarbonate interaction parameter from reference 15. That's the Harvey 84 paper. And there's actually a typo in that original paper. So there's a decimal place, decimal error. And so I had to I yanked that piece of database out and replace it with a different source. So from my perspective, the Miami model was really limited in the way we could use it because it was an Excel sheet and because there were inconsistencies in it. My implementation of it is an even simplified version of it, but with corrections. And MarChemSpec is, in my assessment, the only comprehensive and fully quality controlled PITSA type model currently available. And it's openly available thanks to David and Simon's work and leadership in this field.
Thank you so much for that. So no questions. I've dropped the link to the MarChemSpec website in the chat. So if anybody in the audience needs a bit of time to think about what exactly it is they want to ask, you can find out how to contact our panelists through that website. And you can also find more background information on the program there. Unless somebody wants to ask a last-minute question. All that remains for me is to say thank you ever so much to our three panelists and to the audience for following. And we hope to see you again soon at OA Week. Thank you so much. Goodbye.
Thank you.